Today we're going to make probability distributions feel real by walking through a set of case studies that sound like situations you might actually run into at work, in schools, in healthcare, or in everyday decision-making. In each case study, we're going to do the same thing. We'll name what kind of question it is, match it to the right probability idea, use StatCrunch or another statistics calculator to compute the probability, and then interpret the result as a statement about what we would expect to happen in the real world. Before we start, I want to say a quick word about calculators. Throughout these examples, I'll describe the steps using StatCrunch, but the same ideas apply if you're using another online statistics calculator. Different platforms may look slightly different, but the information you enter and the meaning of the result are the same. What matters is understanding what you're asking the calculator to find, and how to interpret the number it gives back. When you're using StatCrunch or another statistics calculator, probability tools are usually grouped by distribution type. For normal distribution questions and Central Limit Theorem questions, you'll use a normal distribution calculator. For binomial questions, you'll use a binomial distribution calculator. In every case, you'll also choose whether you're finding a probability less than a value, greater than a value, or between two values. That wording is important because it tells the calculator which part of the distribution you mean. Let's start with discrete probability, because this is the only situation where we're not using a curve or a built-in calculator tool yet. We're working directly with known probabilities. Imagine you manage a school cafeteria, and you've been tracking how many students ask for a second serving during lunch. Over several weeks, you notice a stable pattern. The number of second servings is usually 0, 1, 2, 3, or 4. You turn that pattern into probabilities based on frequency. For example, the probability of 0 second servings might be 30%, 1 might be 35%, 2 might be 20%, 3 might be 10%, and 4 might be 5%. The cafeteria manager's real question is not, what will happen today, but, how many extra lunches should I prepare most days without wasting food? That question becomes, what is the probability that at most 2 second servings will be requested? At most 2 means 0, 1, or 2, so you add those probabilities together. When you do that, you get 85%. Interpreted in real terms, that means about 85 days out of 100, preparing 2 extra lunches will be enough, and about 15 days out of 100, it won't. That's how discrete probability supports planning decisions. Now imagine a second discrete example in a workplace setting. You manage a small distribution center and track how many packages arrive damaged each day. Based on past data, you've created a probability distribution for 0, 1, 2, or 3 damaged packages. You want to decide whether to schedule an extra staff member each day to handle damage reports. When you add the probabilities for 0 and 1 damaged package, you find the probability is about 80%. That tells you that most days 1 or fewer packages are damaged, and only about 20% of days require more attention. That's the kind of insight discrete probability gives you. Now let's move into binomial situations, where we rely on a calculator. Binomial probability is used when something repeats a fixed number of times and each repetition has only 2 outcomes: success or failure, yes or no, pass or not pass. The probability of success stays the same, and each trial is treated as independent. Imagine a customer service center that tracks whether calls are resolved on the first attempt. Based on long-term data, calls are resolved on the first attempt 60% of the time. A supervisor reviews 10 calls from an employee and finds that 8 were resolved on the first attempt. The supervisor wants to know whether 8 out of 10 is unusually strong performance, or something that could reasonably happen by chance. This is a binomial situation because there are 10 trials, each call is either resolved or not, and the probability of success is assumed to be 60%. In StatCrunch or another statistics calculator, you would choose the binomial distribution tool, enter the number of trials as 10, enter the probability of success as 0.6, select the option for exactly, enter 8 successes, and then calculate. The calculator returns a probability of about 12%. Interpreted in plain language, That means that if the true success rate really is 60%, then getting exactly 8 successes out of 10 happens about 12 times out of 100 sets of 10 calls. That tells the supervisor that 8 out of 10 is a strong result, but not so rare that it proves exceptional performance on its own. Now imagine a manufacturing example using the same binomial logic. A product passes inspection 90% of the time. A supervisor checks 12 items and wants to know how likely it is that exactly 10 pass inspection if the process is operating normally. In a binomial calculator, you enter 12 trials, a success probability of 0.9, and exactly 10 successes. The probability that comes back is about 23%. That tells the supervisor that seeing 10 passes out of 12 is very plausible under normal conditions, and not a sign of a problem. Now let's move to normal distribution situations, where we're working with continuous measurements. Normal distributions appear when values cluster around an average, with fewer observations farther from the center. Examples include test scores, times, weights, and amounts. Normal distributions appear when values cluster around an average, with fewer observations farther from the center. Examples include test scores, times, weights, and amounts. Imagine a bottling company that fills 16-ounce sports drink bottles. The company tracks fill amounts and finds they follow a normal pattern with an average of 16 ounces and a standard deviation of 0.2 ounces. A contract requires that at least 95% of bottles fall between 15.6 ounces and 16.4 ounces. The manager wants to know whether the current process meets that requirement. This is a normal distribution problem because fill amount is a continuous measurement. In StatCrunch or another statistics calculator, you would choose the normal distribution calculator. You enter a mean of 16 and a standard deviation of 0.2. Because the requirement is between two values, you choose the between option and enter 15.6 and 16.4. The calculator returns a probability of about 0.95. Interpreted in real terms, that means about 95 bottles out of 100 are expected to meet the contract requirement. The manager would interpret that as meeting the requirement, but with little room for increased variability. The probability becomes a tool for monitoring process stability. Now consider another normal example. A warehouse tracks how long it takes to load a truck. Loading times follow a normal pattern with an average of 40 minutes and a standard deviation of 5 minutes. The manager asks how often loading takes longer than 50 minutes. In a normal distribution calculator, you enter mean 40 and standard deviation 5, choose greater than, and enter 50. The probability comes back at around 2 to 3%. That means only a few loads out of 100 take longer than 50 minutes, which helps the manager distinguish between typical variation and unusual delays. You can also use the same calculator to answer a different question. If the manager asks how often loading times fall between 35 and 45 minutes, you choose between and enter those values. The result is about 68%. That tells the manager that most loads fall in that middle range, which helps set realistic expectations. Now let's look at situations where the Central Limit Theorem applies. These are still handled with a normal calculator, but the interpretation is different because we're talking about averages. Imagine a clinic that tracks appointment lengths. Individual appointments vary a lot, but the average appointment length is 20 minutes with a standard deviation of 8 minutes. The clinic schedules blocks of 36 appointments and wants to know how likely it is that the average appointment length in a block exceeds 22 minutes. This is a Central Limit Theorem situation, because the question is about a sample average. In StatCrunch or another statistics calculator, you still use the normal distribution tool. You enter the mean as 20. For the standard deviation, you enter the standard error, which is 8 divided by the square root of 36, or about 1.33. Because the question asks about exceeding a value, you choose greater than and enter 22. The probability comes back at around 6 to 7%. Interpreted practically, that means that about 6 or 7 blocks out of 100 will have an average appointment time above 22 minutes. That helps the clinic decide whether to build in buffers or adjust scheduling expectations. Now imagine a grocery store tracking checkout times. Individual checkout times average 6 minutes with a standard deviation of 3 minutes. The manager wants to know how stable checkout is across groups of 25 customers during busy periods. Specifically, they ask how likely it is that the average checkout time exceeds 8 minutes. This is again a central limit theorem question. In a normal calculator, you enter mean 6. The standard error is 3 divided by the square root of 25, which is 0.6. You choose greater than and enter 8. The probability returned is extremely small, less than 1%. Interpreted in real terms, that means seeing an average checkout time above 8 minutes across 25 customers would be very rare if the system is operating normally. If it happens regularly, it suggests a real change in the process, not just random variation. Across all of these case studies, the key takeaway is that probability distributions are tools for reasoning about uncertainty. Discrete probability organizes known outcomes. Binomial probability evaluates repeated yes or no situations. Normal distributions describe continuous measurements. The central limit theorem explains why averages are more predictable than individual values. StatCrunch or another statistics calculator performs the computation, but the real skill is choosing the right model and clearly explaining what the probability means in context.